Well, I want to thank the organizers for organizing this wonderful conference and giving me the opportunity to speak. I want to talk about fractionalization due to orbital geometric frustration. And before I go into the talk, I should acknowledge my collaborators. Most of what I'm going to talk about is really led by my former student Kevin Zhang and our wonderful Beta Kick fellow Dan Mao. And we had fun collaborating with various colleagues, including experimental group of Mark and Jeannie. Something that I'm not going to do is Hartree-Fock, because enough people are doing Hartree-Fock. But in my discussions with people, I realized that, thinking about crystallization is it could be kind of new to some people. So I just wanted to kind of lay down what are principles of crystallization. Obvious, intuitive stuff, but if you think about it, it's helpful. First of all, in order to crystallize and form an incompressible state, you need to have some level of long-range interaction. If the particles cannot see each other at a distance, there is no way you can form an incompressible state. When you have different gates, whether it's top gate or dual gate, that's going to cause different degree of screening. It's going to make a difference. Finally, lattice potential matters. Without lattice potential, you cannot talk about filling. So, integer filling, fractional filling, that requires thinking about lattice potential. Now, these are all things that you all know, but it's going to be important to keep these things in mind. So, with those in mind, what I want to talk about is new physics of fractionally filled incompressible states at term number 0, that is time reversal symmetric. Fractionalization has been sort of a long obsession of mine, and we all know Hamiltonian involve kinetic energy and interaction, but often when we talk about fractionalization in the context of fractional turn insulator, and you add more adjective to it, it's always starting from the single particle physics. So you start from kinetic energy, the quantum mechanics of non-endowed levels, and then you ask, if I have this gap from the single particle physics, and I partially fill this and add interaction, what can I get? But if you can be in a different setting of having a many-body degenerate state due to strong interaction, that could be a different route of getting fractionalization, and that's the usual way people think about geometric frustration. So what is geometric frustration? The sort of a very common textbook example is Ising antiferromagnet on triangular lattice. When you try to put your third spin, it cannot be up or down. Both are unhappy or equally happy. That's where degeneracy comes. And this notion of geometric frustration has been a very fruitful way to think about magnetic systems, insulators. You think about spin singlets, and you can ask, what can you do with those dimers? You can start asking what is the effect of quantum fluctuation by resonating them. But this is all studied by people who think about insulators, spins. So, we've got our electrons. Electrons have, as you all know, spins and charge. With spins, you can talk about this kind of geometric frustration. Can you also think about geometric frustration with charge? Our kind of mental image of electron is kind of, if you don't think and ask, if someone asks you what does electron look like, and if you're not thinking, you might say, well, maybe it looks like a ball. Maybe it's fuzzy. Of course, we know there are notion of orbitals, which has shape. So the question is, can the shape of orbitals give you a mechanism of thinking about geometric frustration? And now, where can this possibly happen? One concrete context to think about this is twisted bilayer graphene, and we've been thinking about this trimer model of twisted bilayer graphene. So it's been already mentioned several times that you cannot exponentially localize the form exponentially localized binary orbitals up to, say, bilayer graphene. Now, if you just look at pictures, like this is the STM data, I think from Steven's group, what you see is that AA sites have, highlighted high density of states. But you also know that when you try to think about this twisted bilayer system, there is no way to get a triangular lattice symmetry, because if you have a triangular lattice, these high symmetry points would have to be behaving in a symmetric way. You can talk about this in many different ways, but one way to just see it in a very plain in a plain site is that, this kind of band structure fundamentally prohibits thinking about triangular lattice. Instead, what you should think about is hexagonal lattice. That's where the single layer graphene is. So how do you think about hexagonal lattice when your wave function is spread out in this kind of geometry? This was figured out very early on, that the right way to think about these binary orbitals, if you give up on some symmetries, you can localize to some degree, and what you get is this kind of fidget spinner shaped binary orbitals. So we've taken this shape, this extended binary orbitals, seriously and started asking, what can that imply? What kind of interaction physics can that imply? And that gets us to cluster charging Hamiltonian. So here, what we're seeing is that, well, if I represent my binary orbital or fidget spinner as a triangle, I of course do not want to put them on top of each other. That will be a very typical on-site U. But I don't want two of the lobes to overlap, so this gray occupation is prohibited. I also don't want even one of the lobes to overlap. So all of these regions would pay price to be simultaneously occupied. This working with extended binary orbital is painful. If you want to think about hopping, it's also very non-local. Interaction, extended, it's painful. But what we've noticed is that if you focus on a specific filling, fractional filling of 1/3, this can be actually pretty simple. That is, at 1/3 filling, it is possible to avoid occupying any of this surrounding area and just pick one BA site to be the center of binary orbital within this hexagonal lattice of BA and AB. And that's captured by this cluster charging Hamiltonian. Now, this cluster charging Hamiltonian is written in this specific form where we say we want to occupy only one of the 6 sites, and that's a very natural way to think about this fidget spinner shaped binary orbitals. But if you just start counting what this means in terms of range of interaction, it means you have not only nearest neighbor and on-site, but you also have second neighbor and third neighbor interaction. So if you are at partial filling, and if you have to take up to third neighbor repulsive interaction, this is actually a pretty natural way to think about your model. Now, of course, there are additional subleading terms, and those subleading terms are going to introduce perturbation to this leading cluster charging Hamiltonian effects. What we found out early on is that this cluster charging Hamiltonian is very interesting. It gives us this extensive ground state degeneracy. And there is an exact solution associated with it using Bethe ansatz. Now, when you introduce this next leading term, because nature abhors degeneracy, this extensive ground state degeneracy is going to be lifted, and we arrive at sort of a phase diagram where when you change the sign of this 4th order term, you can go from one type of crystalline state, this is a charge order crystalline state, √3 by √3, or another type of crystalline state that we called brick wall. So we were able to understand the limit of pure cluster charging interaction limit, or we also call no-touching limit. In that no-touching limit, there is extensive ground state degeneracy that scales like L square, and you can understand that degeneracy or entropy as coming from this breeding entropy, where if you try to flip one of the orbitals, trying to have one flip will cost our touching interaction term, but you can cause this kind of flip line that is an extended defect that connects you from one legal configuration to another legal configuration. So you can connect various configurations in your extended ground state, and that's one way to understand this extensive entropy. So this paper is the StatMag approach to trimer models already has established that there is extensive ground state entropy, and you can calculate the entropy using Bethe-Ansatz solution. It is an exactly solved model. But what the Bethe-Ansatz solution does not tell us is what is the nature, what is the correlation function like, and what kind of excitations you can have. So now, up until now, I've been talking starting from a simple observation that, well, this, Wannier orbitals, when you Wannierize by giving up on some symmetry, has this extended extent and shape. The question is there a reason to give special attention to one-third filling? And that, if there is going to be a reason, it will have to come from experiments. So from early on, it was noted that when you study the superconducting dome of, this was, I think, magic angle twisted bilayer graphene, there is a dip. There's this dip. And this sort of a dip and suppression of the superconductivity is something that people who's been thinking high TC cuprates are pretty familiar with, that there is a charge order. So when I saw this dip, I asked Pablo, what is the filling at that dip? I was thinking some commensurate filling, like one-third. Third seems natural because of the symmetry of the system. And the number that he gave us was actually pretty close to a third. And then it continued. This is a paper from MIT Harvard collaboration where they reported various churn insulating states, like early days of churn insulator, which required magnetic field. What we noted was that there is this churn zero incompressible state. And as we started exploring what are the implications of thinking about this orbital frustration, we got contacted by Ginny and Mark, who told us that, I think we might be observing what you guys are talking about. So this is transport data. And what you can notice is that this conductance is suppressed at various third fillings. This is at larger twist angle. They have done experiments, they've looked at near magic angle and larger angles, 2 devices at larger angle and 1 device at magic angle. They all exhibit 1/3 incompressible states, but magic angle data is much more complex because there's a lot more going on. If you go to larger twist angle, these 1/3 insulating states are all that's remaining. Now that is actually somewhat different from charge order observed in TMD, hetero TMD system, which shows a whole bunch of commensurate fillings. So what this data really shows is that there is something special about 1/3, at least from this perspective. Dan and Kevin and I had great fun working with Ginny and Mark, trying to see how we think about these various fillings that are not just 1/3 that we already knew how to think about. And having other 1/3 fillings gives us richer set of possibilities, but it's the sort of the same kind of principle. The principle is if you have filling that is different from 1/3, we're going to figure out what you do with the excess, and then you can think about a third. So, but that's fine, that there is a way to get an incompressible state that is not using sort of nesting or Hartree-Fock kind of mechanism, but starting purely from strong coupling approach. and that's kind of cool. But the title of my talk was fractionalization. It had fractionalization in it. So that's where I want to get to. So we know that there are these incompressible states. Beyond it being sort of an interesting way of getting an incompressible state, or sort of a decorated version of maybe something like Wigner crystal, but with the lattice, is there something new to this? And that gets us to fractionalization. So first thing that Dan observed when I started telling her about this when she joined Cornell is that she said, well, you know, if I have this is root 3 by root 3 state where I have removed one electron, so one hole, I can start rearranging my orbitals. Now, this is all insulating state, so I can think about sort of configuration. I can start rearranging my orbitals. And what I am effectively doing is creating 1/3 charged particle. And I can make it move. Now, it turned out in the root 3 by root 3 state, this monomer or fractional charge is confined. That is, energy cost grows with the distance. However, in the brick wall state, you can actually have this monomer move away from each other without paying the cost that grows with distance. That is, the monomers are deconfined. And you can understand this because this brick wall state actually has essentially two slant directions in each layer, the way the bricks are laid. And the domain wall hosts this 1/3 charge. The 1/3 charge is bound to the domain wall. This is a little bit like, you know, SSH. Now, this charge can actually start moving because now what I have to do is between the two slants, I have created two domain walls. So in the brick wall state, this 1/3 charge is deconfined, but only along one-dimensional direction. So this is mobility or movement that's only allowed in a subdimensional setting, and that's called line-on in the language of fractons. So it turned out that this 1/3 charge in the brick wall state behaves as line-ons. So as we started to understand this, what we realized is that this physics of these trimers is a little bit like dimers, but not exactly dimers. We have to kind of figure out how to work with this and think about the implications and predictions for these trimers. And as we were thinking about this, I ran into Roderick at a conference and we started brainstorming together. How can we study this? Especially at J4 equal to 0, that is the exact cluster charging limit where you are in between two charge order states. Now, we're talking about classical physics here, strong coupling limit. So one would think that, well, why don't you just do Monte Carlo simulation? But the problem is, anybody who's thought about Monte Carlo simulation of these geometrically frustrated systems would know that because you have this extensive degeneracy at J4 equal to 0, you got to be able to cover all those states. You need to be able to access different states that are not accessible through local move, because I need this global flip line. So we need to come up with global update schemes, which is what Kevin did. In addition to the scheme that Roderick recommended, Kevin, as he was doing simulations, he realized he needs additional global update schemes. So he implemented these two global update schemes, and which that allowed us to survey the full finite temperature phase diagram. So this is the full finite temperature phase diagram. The horizontal axis is the next leading interaction, next leading to the cluster charging, that's J4. Negative J4 gives us this brick wall state, and positive J4 gives us root 3 by root 3 state. And these were states that we could reason by just making drawings in our early days of investigation. But by doing this full Monte Carlo simulation, we were able to study phase boundaries and order of transition between different phases we also discovered a new intermediate order phase that has recovered translational symmetry compared to root 3 by root 3, but it breaks the it has a polarization. It breaks the Z2 symmetry associated with polarization. And we were able to just study in a very classic sense the order of transition. These are second order transitions, and this particular transition, it belongs to three-state Potts model universality class. There is a first order transition here, and there is a tricritical point. So studying these kind of transitions in the phase, mapping up the phase diagram was rather fun and satisfying and exciting. But most interesting thing was found near the J4 equal to 0 going up to the finite temperature. What we weren't able to answer with the exact solution is what is the nature of this state from the perspective of our fractional excitations, and whether it is a liquid-like state or it is a gap state. And our Monte Carlo studies kind of reveal that what is the nature of this state that is a liquid state. So for large J4, the first order melting we study by looking at various finite size scaling, calculating Binder cumulant, and we can look at the order parameter. This kind of energy histogram establishes that this is a first order transition. And in this root 3 by root 3 state, we can now calculate the correlation function to confirm that the monomers are confined in this root 3 by root 3 state. This is showing the correlation of monomer dimer exponentially decaying. In the larger J4 limit, where we have two transitions, we could map out the second order transition by calculating the susceptibility. In the J4 less than 0, where we have deconfined monomers, the calculation of the correlation function reveals that the correlation is extended only along this the direction that is one subdimensional, and this is showing that indeed the correlation is not decaying. So these are all sort of finite temperature properties that we are able to map out. But most exciting sort of things that we've uncovered had to do with this algebraic trimer liquid state. So J4 equal to 0, this is the cluster charging limit. Trimer liquid at finite temperature. So this is showing, this instead is showing the correlation function. And what you can see in this log plot is a power law decay. There's a power law decay of correlation function. These are at various finite temperatures. You can see that the power law behavior is associated with the 0 temperature limit, but it is extending up to finite temperature. For U of 10 millielectron volt, this would mean that up to about 10 Kelvin, you should be able to observe this algebraic correlation of the monomers. So now we look at this monomer-monomer correlation, looking at sort of a structure factor or correlation function in momentum space. What we see is something that's very featureless. This is what you expect in a liquid, something featureless. You just see the lattice peaks. And we look at the, introduce one trimer hole and look at a correlation function, which is giving us this power law behavior. And you can see a specific exponent here. This is minus 0.25, so it's a minus a quarter. So up to this far was telling us that, well, we've got some algebraic liquid state, which is, have seen in other problems before. Surprise came when we looked at introducing two trimer holes. So now we are looking at two trimer holes, and here is a correlation function as a function of conformally rescaled distance. And if you look at this correlation function as a function of distance, it is sort of oscillating, but each track is giving a specific exponent. So there is one exponent here, minus 0.24, and here's another exponent, 0.47. Now that's very weird. This was a very unusual observation. So then we set out to try to understand how to think about this. First of all, looking at a trimer-trimer correlation, this is like if you could do X-ray on a system and look at a structure factor, this is what you should see. What you're seeing in this trimer-trimer correlation is that there is no additional superlattice peak, that is, this is a liquid state, but there is sort of a pinch point behavior. So this pinch point phenomena tells us there is sort of emergent U1 gauge theory. But there are two pinch points. So there's one here, one here. That means there are two emergent U1 gauge theories. That was the first hint that there is something really interesting about effective, long wavelength effective theory of this system. Now, trimer-trimer correlation power law is something that we can also obtain, and this is power law that we get. 2, -2, roughly that's the -2. So we had all these results. We were able to do large-scale numerical calculation, and we had all these results, and puzzle that we wanted to understand. And that's when we needed to really grapple with, like, how do we think about these trimers? It's something that's pretty similar to dimers, so we should be able to leverage that all the community have invested in dimers, but it is not exactly dimer. And that's, it's really all credit due to Dan, who figured out how to think about this in a very satisfying and really pretty way. So what she said was, after trying many different things, is that, you know, we should map the trimer into 3 interpenetrating dimer models. So now 3, I usually don't like to use RGB, but in this case, RGB made so much sense. So we have blue honeycomb lattice, if I can see this. So there is blue honeycomb lattice. This is a blue honeycomb lattice. And there is green honeycomb lattice. And there is red honeycomb lattice. So we're thinking about 3 interpenetrating honeycomb lattices. And we modeled the trimer as configuration of 3 conjoined dimers. So there's blue dimer and green dimer and red dimer that are joined together to form one trimer. Now this mapping allows us to leverage what is known about effective field theory of dimer models. But because, although there's 3, because they are coupled, that means there will be effectively only 2 independent degrees of freedom. Another thing that we can notice when we just introduce a hole, this is a monomer. So we introduce monomer the way you would introduce monomer in a very typical dimer model setting. So the way you introduce monomer in a dimer model setting is that every site without monomer is supposed to be touched by one dimer and one dimer only. Introduce monomer, there will be a site that's not touched by any dimers. So here is a monomer of our trimer model. And you notice that this monomer is a monomer in the green dimer configuration. And it's also a monomer in the blue dimer configuration. So there is sort of a 2 charge that it is carrying. And the monomers of our trimer model, that is our fractionally charged excitation, E/3 excitation, violates dimer constraint in 2 colors. So I can label this monomer as BG because it's violating dimer constraint in the blue and green. This is GR. Once we got to that point, we were able to leverage the height mapping that was developed early on, especially with contributions from my late colleague, Chris Henley. And what you do is you start assigning height in a way that you go around the site and it goes up or down depending on whether you're crossing a dimer. Now, this is a well-known sort of mapping formalism. What it gives you is a field theory of this height model, height degree of freedom. And it allows you to also think about the dimer field correlation function as a gradient in the height. And you can get the correlation function of the dimer field as 1/r squared. And the monomers form a Coulomb gas. This height field winds around monomer. Once you have monomer, monomers are like vortices. you cannot assign single valued high configuration. But if you separate out the smooth part from a singular part, you can go through this Coulomb gas formalism. And you can even use dual field to do the duality transformation and use the dual field to calculate the monomer correlation function, which is represented as a vertex operator. So this is all known for the dimers. Now I'm almost done. For the trimer model, what we have to do is to recognize that we have 3 colored dimers, but they are coupled. So in fact, only 2 are independent, and you can form orthogonal representations of 2 bosonic fields. And what you will notice is that the trimer correlation function will behave like dimers. So that explains one of our power laws, 1/r² that we observed in the trimer correlation. In the monomers, we had 2 power laws, and that's what remains to be explained. Now, when we think about our monomers violate 2 colored configurations of dimers, and these are 3 different types of monomers that we can think about. Now, if you introduce and another thing to keep in mind is that 3 monomers of different color combine to form a trimer. Unlike in the dimer case, 2 monomers combine to form a dimer. With the trimers, 3 monomers come together to form a vacuum. So if you have only 1 monomer, you are necessarily going to be looking at different monomer types correlation. But if you have 2 trimers, you might be looking at a same type of monomer correlation. When you have same type of monomer correlation, this can be read off from the dimer model literature. When you have different types of monomers, now you have to work with these fields and calculate the exponent, which is pretty straightforward to do if you are familiar with this whole technology or the tool or scheme. So now what we accomplished is not only we were able to confirm a rather novel type of algebraic liquid state where there are 2 different types of exponents, we were able to explain this through analytic calculation with effective field theory. And this establishes that our 1/3 charged monomers of our trimer liquid state are bionic, meaning they are colored or charged under 2 U1 gauge theory. So now I've used various different vocabulary associated with various types of fractionalization. There was fractional charge, there was line-on, there were monomers, and perhaps the number of vocabulary that I've used kind of summarizes into that the trimer liquid state where we have algebraic correlation turns out to be at the cusp of various fractonic states. This trimer model of orbitals is something that you can get concretely out of linearizing BM model. But if you think about it from the cluster charging Hamiltonian perspective, what it means is that it's about the range of interaction. So if you control screening, you can control the range of interaction, and you can find yourself in different settings where up to what order of interaction matters. If you just have up to 3rd order, that's the cluster charging limit, where we talked about the trimer liquid. But if you go to one next level, with J4 less than 0, we already established that it is a line-onic state. When you go to J4 positive, that was √3/√3, where the monomers were confined. But if you introduce further range interaction, that kind of undoes the cost of having these monomers separated, you can get to fractons with sub-extensive ground state degeneracy. If you go to even further range, you can even get to a situation where you have rank 2 U1 cross U1 emergent gauge theory. So my time is up, and I would like to summarize in simple equations. First, 3 is unequal to 2. Everybody should be able to remember that. Trimers are different from dimers. 3 is greater than 2. Physics of trimers are richer. It is a natural way to think about charge order in twisted bilayer graphene. You do not have to tune into magic angle. It's actually even more robust at larger twist angle. But you may not even need twisted bilayer graphene. If you control the degree of screening, or if you have a setting where you can control interaction, and where the interaction is naturally longer ranged, for instance, some Rydberg system, this is a setting that you can get into. Finally, the most, I don't know which equation is the hardest, actually. I have to ask my kids. I have to ask my 9th grader and 6th grader which of these equations are hardest. Anyways, the last of the 3 equations that I want to end with is that 3 minus 1 is equal to 2. Now, can anybody guess what comes as a text if you've been awake? I buy you coffee for guessing this. What is this equation about? 3 minus 1 equals to 2. Yes, David?
How many A fields there are?
Yeah, exactly. Awesome, thank you. Right, so 3 colored monomers. We started with 3 colors because trimer requires 3, but they were conjoined. So there was a constraint that binds them together, which leaves you with 2 independent gauge degree of freedom, emergent gauge degree of freedom. That makes these bionic. With that, thank you for your attention. Oh, one very important, very important slide. We are hiring. We have 2 postdoctoral fellows, 2, 3, large number of postdoctoral fellowship positions. We have a very early deadline because one of the fellowship is at a college level and it requires nomination, etc., some bureaucracy. If you are interested in these positions or, fellowships or individual PI, there are many postdoc positions. It should all come to this AJO. So with that, now really, thank you for your attention.
Yeah, thank you, Una. Let's move to questions.
So Una, I had two questions. The first one's maybe very short, which is when you showed the data on the transport data for the 1/3 states in the twisted graphene system, did I see correctly that the 1/3 dips were more prominent than the integer ones? And do you have an understanding of that?
Ooh, sorry. There must be a better way to do this. There. That's the data.
So, for example, at 2, well.
So
yeah.
the most prominent here is 1/3, right?
Right.
1/3 is very prominent. This is 1/3 is very prominent. Why are they stronger than integer? Actually, at this larger, this is not magic angle, right? So when you go away from magic angle, integer things seem to kind of become weaker or go away. The only thing that remains away from magic angle, based on what Ginny and Mark have explored, is these 1/3 states. That's what we see. Yeah. Why is that the case? I guess that's more a question to people who understand integer states better.
And the other brief question was on what does it mean to have a positive exponent for the correlation function?
Very good, thank you. So positive or negative is a matter of whether you're looking at, so in a dimer model case, it's very natural to think about dimer as 2 monomers, which are like vortex and anti-vortex bound. So when you have a negative correlation, negative power law, that means they are kind of attracting each other. So positive, the vortex and anti-vortex attract. But if you look at vortex-vortex correlation, they grow because they repel. So the sign is about attracting versus repelling. But it's sort of a little more complicated when you have 3 summing to 1.
So I have a question mostly about the last part of your talk. So I guess one can ask the same question about your phase diagram too. So is it possible to tell what's the effect of finite temperature?
From effective field theory
Well, for example, what happens? Well, I guess maybe you get some correlation lengths for your power loss, and maybe there is some interesting dependence of that length on the temperature.
Oh yeah, so at finite temperature, so this primal liquid state extends to, how do I get to there? Right. So if you have a good eye to see this, what you see is that as you go up in temperature, this power law correlation stops at some distance. And that's what you see. So that's why when I describe this quantitatively with 10 MeV as a U scale, you get up to some tens of Moiré lattice constant at, 10 Kelvin. That's the translation of this into numbers. Does that answer your question?
Well, partially, but I wonder, you probably do, so you get this correlation length. Is it possible to tell about that correlation length, how it depends on the temperature? That's maybe a more concrete question.
I only have it from simulation. So this is finite temperature Monte Carlo simulation, right? And you see that, correlation function plotted as a function of rescaled distance, at very low temperature, it just continues on. But at higher temperature, it kind of saturates. That's the extent of our understanding.
Thank you.
But it's kind of, I guess, typical. Yeah.
Thank you.
Yeah, we're going to do this question, but given that your modeling and all the calculations are classical stat-mech calculations, presumably the descriptions of this kind of system at some temperature scale above some quantum exchange scale, right, but still below some scale where local charge ordering sets in. Right? Would you agree with that?
Sorry, what do I want to agree? I want to agree with you generally. What am I agreeing?
We're doing a classical stat-mech problem.
Yes.
So in terms of applying it to
quantum problem?
Yeah, so it's above some quantum exchange scale, but below some scale of local charge ordering.
Right. Yeah.
So in that sense, it's intrinsically a finite temperature story.
Right. It's a finite temperature story,
right.
Yes.
So do you have any understanding of the
what happens if I go to zero temperature, like really quantum, like tough
the quantum
to be real? Yeah. Okay.
No.
Yes. So.
And related to that, in the experiments that you showed, do you know whether they are in a classical regime or in a regime where quantum exchange is important?
So from experiment, all we have is a gap scale from transport. And the gap scale from the transport was kind of, making sense with thinking about our charge order state, the level of incompressibility given the parameters that we know. But, no, I don't have a quantitative answer. Nevertheless, I am interested in quantum problem. And there are several angles that we are thinking about. One kind of obvious thing is, everybody, you start talking about timer model, they will say, well, why don't you do resonating, right? And you actually already probably know, but, the part of our 3 greater than 2 is that trying to resonate is also kind of non-trivial. But we have thought about, what would you have to do to get to part of the ground state configuration that is sort of a sensible kinetic energy that couple within your degenerate manifold, and it turns out to be this big object called Lemnis gate operator. We named it. You can look up the word Lemnis gate. It's this number 8 sideways or infinity symbol. But this is one way if you want to try to extend this to follow the program of quantum dimer model. This is how one would go. But there are other things that one can do. Something that I started with, which was this sort of a grand vision, how do you think about fractionalization differently? So here, we have a setting where we have extensive ground state degeneracy. Now we know, say, FCI, fractional churn insulator, would mean that there should be only 3, like 1/3. So can I think about going from this sort of state to FCI-like state? What would that require? That would require, if I am to do something like ED, the spectrum to go from looking like this to just 3 remaining and the rest lifting up. And we have some preliminary results that shows that you can achieve something like that. So we can have a transition between our fractional correlated insulator and fractional churn insulator. And that is being pursued with exact diagonalization and PEPs in collaboration with TIRUS. So these are different ways of trying to approach quantum problem.
Okay.
Is there a very interesting talk? Is there an order by disorder calculation?
We don't have order by disorder calculation yet. It's again not easy, but if you have good ideas, we would love to talk about this. So another thing we're looking at is like quantum fermions are hard, so we're thinking of a quantum boson with this model, but we don't have, short answer, we don't have a calculation yet, but that would be very interesting to study.
Yeah, thank you very much. So it reminds me a little bit of in the bulk materials, there are some systems that form this type of molecular orbitals, so triangles, and then you can also start playing with these type of trimers.
Right, right.
Though there they are, I think, much more localized because they
Right.
form these molecular orbitals. But it's a very interesting idea that one could think of even extending that to the bulk materials.
Yeah,
because there you have
absolutely,
lots of these type
yeah.
of three building these type of states.
Right. So indeed, it would be interesting to think about this kind of objects that have shape, and what would geometry, frustration physics, all that we've invested in from spin physics can help us. What kind of progress can it help us make? And it doesn't even only have to be like triangular lattice. You can think about, say, square lattice too. Like the whole idea is there is one extreme limit of Coulomb interaction. That's infinite range. And there's another limit of Hubbard model. But there's in between, you can think about, of course, what we are familiar with is what does single gate look like, what does double gate look like. We know that. But now we live in this new world of, being able to think about cook-up lattice models. And, if you're not doing 2-DEC, but you're thinking about these kind of lattices, thinking about the different rich physics that you can get with possibilities of extended interaction takes up a whole new dimension. And we were kind of surprised. We're still every day still getting surprised at how much there is to do, like how rich this is. It's just very interesting and fun. Yeah.
Okay, it's time to have a break. Let's thank Una again.